and that's around the whole subject of big data and the use of things like AI, machine learning, and how we utilize the data from refrigeration systems. So in terms of future trends, this is going to touch on what's been happening over the past sort of 5 or 6 years, and how that's then going to affect what we do within our industry moving forwards. But data is something that we've had available for quite some time. If we think about it in my own business, we've been using data from refrigeration systems since the early 1980s. And that data has been used to show what temperatures and pressures and kilowatt hours previous day a refrigeration system has been using to give us an idea of how a plant is performing. As that's progressed over time, the technology has moved on. Moving on of that technology means that we can collect more data, we can collect it in real time. And what I'm going to talk about this morning is something that we've implemented across something around about 93 sites in the UK and increasing each month. And just to give you a scale of what this is we're collecting over 40 billion pieces of data each year. We're analyzing that data, and the whole drive of that data through a mixture of machine learning, AI, and manual analysis is driving down energy consumption. And we see that as a trend that's only going to increase as the years move on. Why is it important? Well, here's an image which was part of a report written by the Cold Chain Federation, which is a trade association associated with temperature-controlled warehousing. The reason I put this up at this point is that if we look along the bottom, it shows different sizes of buildings and at different temperatures, whether they're frozen buildings, chilled buildings. But it actually demonstrates some of the challenges that we're seeing within the industry, and it also shows the opportunity that we've got through use of data and technology like AI. Up against the y-axis, well, these various stores consume a certain amount of kilowatts per meter cubed of volume per year, and the blue columns show the benchmarking depending on the temperature and the size and the expected kilowatt hours per cubic meter for that facility. Now, the red shows that some of the highest energy users within that particular sector, and the green shows the lowest. Now, if you take the small chilled facilities as an example, a small chilled low energy user is probably using something in the region of 70 kilowatt hours per cubic meter per year of energy for that facility. A high energy user is using over 210, probably closing in on 220. So there's a difference of 3 times between one energy user and another. They're both maintaining a facility that's a similar size and at a similar temperature. Why the difference? Well, one of the key ones is the operation and performance of the refrigeration system, often which is based upon a proposal written on a piece of paper, which is then commissioned and set to run, but very rarely then is any further analysis carried out on its performance over its operating life. But what we can see is that there's a huge scope across all of these facilities for improvement in energy efficiency. So why move towards this? Well, as an operator of those facilities, one of the big things is that we've seen energy costs increase threefold, probably in the last 5 to 10 years. So there's a desire to get energy consumption down because it's costing a lot more to purchase that energy. At the same time, operators have made commitments in terms of net zero and sustainability, which they need to meet defined by a certain timescale. But if you bring those two together, what you have is a real competitive advantage, because if you are able to reduce your energy costs for running, if you're able to demonstrate your sustainability, it gives end users a competitive advantage. So that's one of the things one of the areas that's really driving this. From our perspective, though, as a refrigeration system, most people focus on the installation cost of how much it's going to cost to purchase a refrigeration plant. Typically, that's 15 to 20% of its life cycle cost. By far the biggest is energy, and then similar amount for the installation cost would be the maintenance over its time. If we can drive down energy consumption through monitoring and using this big data that we're already collecting, then we can reduce the overall cost of ownership of the refrigeration system. And this is where real focus needs to be placed over the operational life of a refrigeration system. So not just purely for nostalgia reasons, but taking us back to the 1980s. Here's a photograph on the left of one of the earliest refrigeration monitoring systems that we as a business installed, and typical for what was available at that time, microprocessor. But you can see these little sheets of paper that it produced each time you ran off a request for data. It would produce temperatures, pressures, and kilowatt hours used previous day. So even back then, when we were collecting data, we were seeing data on energy performance. The photograph on the right is the sort of next generation of that. And as we roll forward to modern day, we have hugely powerful control systems, typically PLC based, collecting huge amounts of data, millions of pieces of data per site per year, often stored on hard drives, reviewed sometimes. Example here, one of our engineers on site looking at the performance of a refrigeration system. But do we really look at that data in depth and analyze how a refrigeration system is operating? Do we optimize and maximize the benefit of the data that we're collecting? And the answer, if we sort of take a long, hard look at it, is probably no, because too often our maintenance and performance analysis is very, very basic. It's often manual readings taken from gauges, maybe from the PLC screen, recorded on a sheet of paper, filed away somewhere in a plant room, possibly back at the office. A lot of it is still done manually rather than actually taking benefit of the huge amounts of data that we've got available to us. And I refer to this as driving using the rear view mirror. We're typically, in looking after refrigeration systems, we're looking historical data, stuff that happened in the past. If you imagine driving the car and just looking at the rear view mirror to determine which direction you're heading, that's pretty much how we're operating refrigeration systems. We only ever look at what happened in the past. We tend to go and look at it when something goes wrong, or an operator says, my energy's gone up 20% in the last 12 months. Why on earth has that happened? There's a scurry around, people go back and we look at the information that's been recorded and try and work out why that's the case. And that can ultimately lead to underperformance that can go undetected for days, weeks, months, and yes, even years. Why? Because we get used to a trend. We get used to a certain level of energy consumption. We get used to what we've seen historically within the data. But is that data right? It doesn't need to be like this. The better way to do it is, and the way you would drive a car is to look at what's coming in the future. You're looking at the front screen of a car to see other traffic, pedestrians, what's happening on the roads. We can do the same with our refrigeration system. We collect huge amounts of data which can allow us to better understand the current performance, but also the future performance of that refrigeration system. We can carry out real-time analysis of that data, which provides insights to say, are we operating optimally at that moment in time? If not, can we implement improvements to address that particular issue? And ultimately, can we use that data to predict future energy consumption? And I'm going to come on to that shortly about how we can actually do that. But I refer this as driving using the front windscreen. We're actually using the data that we collect on a day-to-day basis to give us a good view of what's happening in the future. And it's relatively easy to achieve with modern day technology that is at our fingertips now. We can collect data from refrigeration systems, whether it's using 5G or a broadband type connection. And by feeding that off-site and putting it into the cloud, that's where the analysis can take place. We can use computer models, we can start to use machine learning and AI to process that data. And when we then process data, we can say, well, how does it compare to what we expected when we designed that refrigeration or air conditioning system or chiller? When we designed it, it was supposed to work like this at these conditions, at this temperature. How's it doing? We can take the real life data, we can compare to what it should be ideally doing and say, well, are there any gaps? Those insights allow us then to feed back and say, well, it's not quite performing here, or this isn't how it's performing as it should do from an energy perspective. Feed that back and make any necessary changes to steer us back onto the optimum performance.